And we can move to the next speaker, who is Andrea Solfanelli, which I'm going to introduce.
Yes.
Here he is. So also Andrea, he studied in Florence, where he had his bachelor and master degree, as we said before. He is a little bit older maybe than Anna, so he finished his PhD, which he did in SISSA in Trieste, in statistical physics at SISSA, under the supervision of Stefano Ruffo. Today, he is a postdoctoral researcher at the Max Planck Institute in Dresden, in Germany, supervised by Marin Bukov. He is expert in quantum technologies and quantum thermodynamics, and in systems with long-range interactions. The title today will be Universal Work Statistics in Long-Range Interacting Quantum System. Please, Andrea, you can share.
Yes, share. Okay, can you see the slides?
Yes, yes.
Okay. Can I start?
Yes, please.
Okay, so thank you for the introduction and thank you for the opportunity to give this talk today. And as it was just said, a few months ago, I used to be a PhD student in SISSA in Trieste, and my supervisor there was Professor Stefano Ruffo, and my external course supervisor was Niccolo De Feno in ETH Zurich. Then now, just in October, I moved to Dresden, so I will acknowledge also my new bosses, Professor Redrik Mössner, who leads the condensed matter division here at the Max Planck Institute for the Physics of Complex System, and Marin Bukov, who is the leader of my new group. Then, as the title says, we are going to talk about long-range interacting quantum systems. So let me briefly provide you with a definition of what they are. So long-range quantum systems are many-body quantum systems in which the microscopic components of the system interact within each other through an interaction energy, which decays as a power law over distance. Then, depending on the value of the power law exponent alpha, we may identify three regimes. If alpha is smaller than the dimensionality of the system, so the power law is very slow, then we will be in the strong long-range regime, in which the system is truly non-additive, and the presence of this power law decay will strongly affect both the equilibrium and non-equilibrium properties of the system. However, this regime is typically somehow a mean field regime, because the system is so fully connected that it tends in the thermodynamic limit to behave in a mean field way. Instead, today, we will focus more on this weak long-range regime, in which alpha is in between the dimensionality of the system D and a certain model-dependent value alpha star. Then in this regime, the system will maintain its quantum nature and its possibly interacting nature. And however, the power law is still sufficiently slow that it will still affect several properties of the system. And for example, if we are at a critical point, it will affect its universal properties by changing the universality class with respect to the corresponding standard nearest neighbor universality class. And finally, if alpha is larger than alpha star, then the power law is too fast, and we will basically retrieve standard short-range physics. Now, from an experimental point of view, just to have a small motivation of why these systems are somehow interesting, especially I will consider the quantum point of view, which is the one I'm a bit more interested in this period. And basically, long-range interacting quantum systems can be realized by several atomic, molecular, and optical platforms. In particular, if we consider cavity systems in which we have atoms into an optical cavity, then the interaction between distant atoms can be mediated by the photons of the cavity. And this may be engineered to realize a completely flat interaction with alpha equal to 0. Then we have Rydberg interacting systems, which display Rydberg atom systems, which display dipolar interactions, or more generically, any dipolar interacting system will have an alpha equal to 3 or to 6. And finally, we have trapped ions, in which the interaction between the spins of the ions is mediated by the phonons of the lattice in which they are trapped, and their spin-phonon coupling can be tuned sufficiently cleverly in order to allow to implement an effective power law decaying interaction with the alpha exponent, which can be tuned in between the value of 0 and 3. And this is particularly nice because it allows to probe both the weak and the strong long-range regimes I was referring to in the previous slides. Now, from a more theoretical point of view, there is a plethora of phenomena, non-trivial phenomena, which happens in this kind of systems. Here I listed just some examples, both more from the quantum point of view. There are novel and non-trivial forms of entanglement, scaling, and dynamics. Both in the quantum and classical cases, we have the presence of metastable states with a lifetime which diverges with the system size. And as I was already referring to before, we can have modified universal properties with non-trivial critical exponents, which depends from the parameter alpha, and many more. And I can refer you to these very recent reviews on long-range interacting quantum systems, which treat the equilibrium property, the first one, and the out-of-equilibrium properties, the second one. Now, end of the introduction, we can move to the main topic of the talk. And the topic of today's talk is basically to try to address these two questions. The first one is, how does long-range quantum systems respond to an external driving? And more precisely, how is the universal scaling of the excitations of the defects, which are dynamically generated if I perform my driving towards a critical point, and how these are modified by the presence of long-range interactions. Now, the reason why these two questions are somehow interesting can be seen from many different points of view. The point of view that I will choose to use today is the one of quantum thermodynamics. So quantum thermodynamics is a field of research in which we try to study the thermodynamic efficiency, basically, of quantum devices, as, for example, here we can see a quantum processor. And therefore, as you can imagine, reducing the generation of excitations during any driven evolution process can be useful in this context in order to reduce the dissipation of energy that these excitations will carry with them. In particular, so the standard setup for any quantum thermodynamic protocol is the following. So we have a quantum system, which is initially into a state rho of I, and it is described by an initial Hamiltonian h of I. Then we would like this system to talk with the external world, so to exchange energy with the external world. And we can do this in two main ways. The first one is that we can allow the system to exchange heat with external reservoirs, or more generically with external environments. And we can have one or multiple versions of them. Then The other possibility is that we can directly apply a drive to our Hamiltonian, and so we take a parameter inside of our Hamiltonian, this h of t, and we let it evolve in time. We change its value from an initial value h1 to a final value h2, and this will drive the system towards a final state rho of f and a final Hamiltonian h of f. Then, if we compute the expectation value of the energy of my system at time t, and we take the derivative with respect to time, then we have we can immediately identify two main contributions. The first one comes from the time dependence of the state of the system, and basically it would be there only if we consider an open quantum system evolution, or an open system evolution more in general. And therefore, we can associate this contribution as the heat that we are exchanging with the reservoirs, if they are present. Then we have the second contribution, which is the one we will focus more in detail today, and which is due to the time dependence of the Hamiltonian, and therefore can be identified as the work we are exchanging with the external driving by changing in time the value of this parameter in our Hamiltonian. Now, even in the simplest case in which we consider an isolated system, so with no reservoirs and only an external driving, which then results into a unitary evolution in the quantum case, still the work variable will be a stochastic variable in general, and therefore we can define its stochastic, its distribution basically. And the definition is very simple. It is basically a superposition of Dirac deltas, which are centered at all the possible differences between the energy levels of the final and the initial Hamiltonian. And these Dirac deltas will be weighted by these probabilities P of n and m. And in the simplest case scenario, in which the initial state commutes with the initial Hamiltonian, these P of n and m are simply given by the product of the initial populations of the different energy levels of the initial Hamiltonian times the transition probabilities between the eigenstates of the initial and final Hamiltonian generated by the unitary evolution associated to the driving. Now, basically, one of the main limitations of any quantum thermodynamic device, and in general any finite time thermal device, is the so-called power to efficiency trade-off. Indeed, we know that in order to have a finite power, we would like our driving to be fast, or at least performed in a finite time. However, we also know that as soon as we perform a finite time driving, then we will face non-adiabatic transitions in between the energy levels of the system during the evolution. And this can be seen also as the generation of excitations into my system, and these excitations will carry with them some energy also, and this energy will be irreversibly lost in the system and cannot be used for any useful purposes, and therefore will necessarily reduce the efficiency, the thermodynamic efficiency of my device. This can be seen also by rewriting the work variable as the sum of two contributions. The first one is the adiabatic contribution, so it's the one you would obtain if you go infinitely slowly in time, plus the remaining part, which is the irreversible work, and it is always positive, meaning that it is always lost into the system, which will be heated up and will necessarily reduce the efficiency of a device. In particular, what we will consider today is the distribution of the intensive irreversible work, which is this irreversible part of the work, divided by the volume of the system in order to make it an intensive thermodynamic quantity. Then, what we would like to understand is what happens to this distribution as I change the value of the power law decay exponent alpha. And what I will try to justify, this is a spoiler of what will happen, basically. What I will try to justify in the following slides is that if I reduce alpha, basically this, and so I am more and more long range because the power law decay is slower, the tails of this distribution in the small W limit, which is the limit I would like to enhance in order to have a more adiabatic protocol, because it's the limit of a small irreversible work. So these tails are enhanced, meaning that the probability of having small irreversible work is enhanced by the presence of long-range interactions. And in this sense, the presence of long-range interactions make somehow the system more adiabatic and therefore more useful in the sense of quantum thermodynamics. Now, in order to study the properties of this distribution, as we typically do when we study statistical distributions, we perform its Laplace transform and we will consider its characteristic function g of s. Moreover, I will consider the simplest case scenario in which the initial state is the ground state of the initial Hamiltonian. And I will also consider the fastest possible quench you can think of, which is the sudden quench, in which you instantaneously switch the value of this parameter from H1 and H2. And if time will allow, I will also say a few words on the opposite limit, which is the slow driving limit, in which I do a ramp at a finite velocity v, and I want to see what happens when I choose a very small driving velocity. Then, since we like universal properties, we will also consider a critical quench. So we will assume that this parameter, the driving parameter, is also control parameter for a quantum phase transition in our model, and the final value of this parameter will also be the critical point of this transition. Now, let's start from the quench case. In this case, the characteristic function can be rewritten in this nice simplified form, which allows for a very nice physical interpretation of this object in terms of a quantum to classical analogy or mapping. Basically, this characteristic function can be seen as a partition function on a system that, due to the presence of these two boundary states in these expressions, will be now in a d+1 dimension, so a classical system in d+1 dimension, but in a bounded geometry, so in a slab geometry where the thickness s is nothing but the variable of a Laplace transform. And then, since we have considered a critical quench, then the correlation length of this system will also go to infinity. And this analogy was first identified by Andrea Gambassi and Alessandro Silva in this paper for the case of local systems. And what we would like to do is to generalize this mapping also to the case of long-range systems. Now, going on with this analogy, since g of s can be identified as a partition function, then taking its logarithm will give me a free energy. And in particular, since I will be interested in the large slab limit, so large S limit, I can expand this free energy in powers of S. The leading contribution is the bulk free energy from the classical point of view, and it is the adiabatic work from the quantum point of view, which in this case is nothing but the difference between the initial and final ground state energies. Then we have the surface free energy, which is the free energies of the two boundaries of my system, and from the quantum point of view, is related to the fidelity, so the overlap of the eigenstates of the initial and final ground states. And finally, we have a subleading contribution, which goes to 0 as S goes to 0, but which is the most interesting one when we are considering a critical quench, as it will take this universal form, which has basically this power law in front, which depends on the dimensionality of the original quantum system, D, times this universal scaling function, which depends on this scaling variable S divided by the correlation length of the system. Now, as I said before, I am interested in probing the large deviation tails of my distribution in the limit of irreversible work much smaller than its expectation value, and this corresponds exactly to the S to infinity limit, so the large slab limit in my slab geometry. Then I can assume that my distribution in this large deviation limit assumes this form, where I have introduced the rate function, which is nothing but the Legendre transform of the free energy I was showing in the previous slide. And now we can use this universal scaling form of my free energy in order to obtain the rate function. And if we go also to the critical point, so we assume the correlation length to be infinity, then we obtain this very simple form for the rate function, and which, as you can see, has a power law dependence on the irreversible work, which crucially depends only on the dimensionality of the original quantum system. Now, in order to generalize this result to the case of long-range systems, we will use an approach, which is an approximated yet pretty useful approach to treat the universal properties of long-range systems, both in the quantum and classical case, which is the so-called effective dimension approach. So this paradigm basically states that if we have a long-range classical system to be simple in D dimensions, then and characterized by a single particle dispersion relation of this form, then this system, the universal properties of these systems can be considered as, can be mapped, somehow can be found as the universal properties of a short-range version of the system in a fractional D-effective dimension, which depends on the power law exponent alpha, on the original dimensionality of the system D, on the dispersion relation of my system, and also on the anomalous dimension exponent of the short-range system in the effective dimension. And so this is somehow an implicit equation for the effective. And then once I know this, basically I have a mapping between all the critical exponents of a long-range system and the one of a short-range system in the effective dimension. Now, I will not have time to give a very precise justification of this approach, and I can refer to you by this paper by Giorgio Parisi and collaborators, in which they give a very nice field theoretical explanation of this fact. But what I will show now is a plot of some data in which you can compare basically the new critical exponent for an Ising model, both a long-range Ising model in 2 dimensions and a short-range Ising model in the effective dimensions. And as you can see, if we scale these exponents properly as predicted by the effective dimension approach, then the matching is not exact, but it is pretty accurate. And in particular, we can estimate this the ratio of the two to be always above 97%. And so I hope that this will somehow convince you that this approach is it works pretty well, at least in this case. Then, once we are convinced of this, what we can do in order to generalize this result for the rate function of the irreversible work statistics is simply to take the short-range case in generic dimension D and to replace D with the effective, basically as given by the formula I showed in the previous slide. And this is somehow a final step of this quantum to classical mapping, which is valid for the long-range case. So I will map my out of equilibrium work statistic problem in a quantum long-range system in dimension into a classical equilibrium problem for a short-range system, but now in the effective +1 dimensions. And once we know this, basically we also know how the tails of the distribution will change. Indeed, the effective dimension is typically larger with respect to the original dimension of the system, because the presence of a long range tends to push you towards the mean field case, and so push the dimension towards the upper critical dimension. And this will result into a stronger dependence of this power law from alpha, which actually results into exactly the into a smaller rate function for a small value of W, which is the regime where this calculation is valid, and therefore a larger probability in this regime. And we can also check this argument by considering an analytically solvable model, which is a free fermionic chain with hopping and pairing couplings, and the driving parameter will be the chemical potential. In this case, since the system is quadratic, we can compute the rate function also from top to bottom without passing from the effective dimension, but the final result matches the effective dimension prediction with the effective dimension, that in this case is 1 over alpha minus 1. Okay, I don't know how much time I have, but maybe I can say a few words also on the opposite limit,
like
which is
2 or 3 minutes. Okay,
so I will be fast. Basically, in the opposite limit of a slow driving, what we expect to happen what happens to the irreversible work distribution is that as the velocity is reduced, this will shrink to a Dirac delta centered at 0, which is the adiabatic point. So basically what we would like to see is how quick this shrinking happens, and if I can do this shrinking faster if I put some power law decaying interactions. And to do so, we can basically compute the cumulants of my distribution and compute them in the small velocity limit, which if we are doing a critical quench again, will have a power law dependence on this velocity, and this power law exponent can be computed by a standard adiabatic perturbation theory, and it is related to the critical, is an universal exponent, which is related to the critical exponents of the quantum critical point we are quenching to. And this can be obtained also again using the effective dimension. And then we have this condition in which if this exponent is larger with respect to the short range one, it means that basically our distribution will shrink to a Dirac delta faster as the velocity goes to 0. And so again, the system will be more adiabatic when long range is introduced. And we checked this that this condition is satisfied both in the fermionic chain I was mentioning before, in which we could also predict basically analytically these exponents, and in the long-range easing, in which we used the effective dimension predictions for the critical exponent that, as I showed you before, works pretty well. Cases we have that this condition was satisfied. So, in conclusion, in this talk, I tried to convince you that long-range interacting quantum systems are somehow cool, both from the theoretical and experimental point of view. I showed why they may be useful in the long-range, in the quantum thermodynamics scenario, and I characterized the quantum Ward statistics in driven long-range systems, and in particular its universal properties. And finally, I showed that both in the fast and in the slow quenches cases, the presence of long-range interactions reduces the non-adiabatic energy losses by suppressing the generation of defects in our system. This is the end of the talk, and I thank you for your attention.
Okay. Thank you, Andrea. Questions?
Perhaps I have one.
Stefano.
Or two.
Okay.
If you can give us some more intuitive explanation of this increasing of the adiabaticity upon increasing the range of interaction, if I understand correctly.
Yes.
The other question is that if this effective dimension is the same thing as a spectral dimension.
Okay, so from the intuition, basically, unfortunately, I don't have the plot here, but basically, most of the properties comes from from how the alpha modifies the spectrum of a system, and in particular its dispersion relation. So if we are considering, for example, the slow quench case, you can imagine that if we go sufficiently slow, then only the low energy part of the spectrum will be populated through non-adiabatic transitions. And then since the alpha modifies the dispersion relation, this part of the spectrum will be somehow shrinked, will be more steeper, and therefore it will cost more energy to generate this excitation. In a certain sense, the system will be more gapped when long-range interactions are present. This is more or less the intuition. Then it is a bit more non-trivial than this, because it is non-trivial why we have the advantage both in the slow quench and the fast quench limit, but more or less this is the general intuition.
So it's the fact that the gaps becomes larger when alpha decreases.
Somehow, yes. Or since we are at the critical point, the spectrum will be gapless in any case. So I will generate some defects, some excitations in any case, and I will break the adiabatic theorem. But since the dispersion relation at the gapless point is more steeper when long-range interactions are present, then still generating defect will cost you more energy with respect to the nearest neighbor case.
This argument should apply also for a non-critical system, right?
For a non-critical system, yes, because you need to check whether your gap is increased, but it will be increased if you put long-range interactions. Yes, we choose the critical point basically only because it allows you to extract all these nice universal scalings and so on.
Another question is about the spectral dimension. This effective dimension is the same thing?
Okay, this is a good question, and I think that the answer is yes. So yes, I would say yes. If you take if you start from the simplest case, which is a non-interacting system, as this fermionic chain I was mentioning before, if you compute the spectrum of this chain and you compute the density of states and you go to low energy, this density of states will scale with the energy at low energy as exactly as the spectral dimension, and the spectral dimension will be exactly the effective dimension. In more complicated cases, it could be more involved, but in general, I would say that yes, they are the same thing.
Okay, grazie, Andrea.
Okay, other questions? Fine. If not, just let me say there is an advertisement that the next seminar will be, usually they are the second Thursday of the month, but due to the holidays, it will be the third, and it happens on day 16 of January. And so we are done. I want to wish you a nice Christmas to everyone, and see you next time. Bye bye.
Ciao, arrivederci.
Ciao.
Ciao a tutti.
Arrivederci, grazie.
Bye.